Welcome everyone. Thanks for joining or staying for the talk. I'm going to talk about like a slightly different topic with quote unquotes on slightly. I'm going to talk about the async code reviews, or most likely on the or on the blocking async code reviews, and why they tend to be such a big problem in product development teams, and why they're such a big obstacle to fast flow of value. Yeah, my name is Dragan Stepanović. I work as a principal engineer, and most of my career I spent at the crossroads of a couple of fields mentioned here. I've been XPeer for quite a long time, theory of constraints, lean and systems thinking, and I try to kind of connect the dots between these worlds. And it's a really fun journey along the way. I tend to rant on the social networks as most other folks. And there's also one quite a terrifying fact about me, especially for the Italian folks in the audience, if we have any, and that is that they put me on pizza for some reason, and just don't ask me why and how it started. But there you go. So not sure how many people heard for this quote. Nobody ever got fired for buying IBM. And I wasn't in the industry at the time. And what I got to learn was that the IBM was quite a big vendor during the 80s. And if you were working as a person in a procurement department of a big company and you needed to procure equipment, then you had a lot of questions to answer if you didn't go with the IBM. And it's a really interesting kind of thing to think about, because I also get it's a very reasonable strategy for minimizing downside risk, meaning that if anything goes wrong, right, who could have thought, IBM, or everyone went with IBM. But if you went with someone else and things went south, then you would likely have to answer a lot of questions. And the reason why I mentioned this quote is because I spent a lot of times working hands-on together with the teams. And one of the things that they get to experience as well is that nobody ever got fired for doing PR-based async code reviews. And for the folks that are not too familiar with what code reviews mean, or what are pull requests, or shorthand PRs, I'm going to walk you quickly through this visual where I try to depict this. So here we have two developers in a team, Em and Luca, and let's say that it's a start of iteration. And Em and Luca are working, I used to say individually, but I changed the language now. I say they work in isolation because I think that reflects the reality better, in isolation from feedback. So Emma is working on ticket number 1 here. And Luke is working on ticket number 2. And if we follow Emma's ticket number 1, and the same thing is going to apply for Lucas or anyone else in the team, what happens is that, let's say that Emma is developing a feature. So she's introducing some changes to the system, and then hopefully testing. And at one point she figures out, okay, I think I'm done, and I would like to invite my peers for a review. So what we usually do is that we raise a pull request with the changes that we made, and we invite our peers for a review. But Luca is busy, so Luca is working on his own ticket. There are lots of other things that are competing for their time. So as you can see here, there's other PRs to review, a bunch of meetings to attend, answering Slack, email, etc. And people are not able to react immediately. And Emma, wanting to be a good employee, so to say, she doesn't want to twiddle her thumbs. So what she decides is that, while I'm waiting, let me start working on something else. So Emma pulls ticket number 3. At one point, she figures that Luke is not responding, and so she tries to remind him in some way. Luke eventually comes around. He reviews the pull request. They go back and forth until they converge on a solution that both of them are satisfied with, and then the pull request gets approved and merged. So this is what I call pull request-based async code reviews. And it's interesting, but I would say it's a gut feeling, but I think north of 95% of the teams in our industry are doing this practice. And unfortunately, this whole way of working has been imported from a completely different context, which is the open source community, which has a completely different constraints, but for some reason we adopted this way of working in a typical product development teams. So if there's one thing that I would like you to take away from a talk is that async by design means delays. So if there are no delays, then it wouldn't be async, right? And having in mind this equal sign here is really important because you have to be very cognizant of the ways that this thing affects the ways of working and how to design how teams work. So what I'm going to talk about today is actually the results of the study that I did over a couple of years, where I analyzed now more than 40,000 pull requests, and the teams have been a typical product development team, so no open source software. And I'm going to share with you the systemic insights that I got. Some of them have been expected, and some of them were even a surprise for me. So just sharing, that's kind of the idea behind the talk. So what was I curious to see? There are a couple of things. The reports that I generate contain way more than what I'm going to talk about today. But these three things really were something that caught my eye, which are about engagement, wait time, and size, and the relationships between these dimensions. So let's go into these one by one. So here we're going to talk about the engagement. And the reason why I got curious about engagement is that I also come from a different background of XP, as I mentioned, where people tend to work way more together than what they get to observe in the wild. And one of the metaphors that I had in my head was that when I have a call with someone, what they tend to observe when there's a delay in communication, for some reason there's delay in the voice between the parties, is that the conversation tends to die out pretty quickly. And that's one thing. And the other thing is also when we talk about the pull requests, they also have a different kind of cost for the feedback because we provide the feedback on pull requests in a written form, which tends to be very much different than what we get to experience as a medium and the quality of the richness of the medium when we have a face-to-face and just-in-time conversation, so to say, or sync conversation. So that's the reason why I also call this way of working the async code reviews a high latency and a low throughput feedback, right? So when we think about engagement, here's the first scatter plot, and on the x-axis you can see the size of the pull request, which is in lines of code. And I use this metric as a proxy for the amount of effort that is invested in creating a pull request. Now, this is an approximation that works in some cases and in some cases it doesn't because there are assumptions behind it. So that's one thing that is really important to have when it comes to the proxy metric. But on average, when it comes to the data sets that I analyzed, the bigger pull requests tend to have more processing or touch time, some metrics from Lean, than for the smaller pull request. And on the y-axis, we can see the engagement, which is here defined as the number of non-trivial comments that we get to see on the pull request. Now, what is a non-trivial comment? So a non-trivial comment is a comment that is not trivial, and a trivial comment is a comment, it might sound silly, but the way that they define it is a comment that has 4 or less words. And the reason for that was that I wanted to filter out all the looks good to me, +1s, thumbs up, LGTMs, etc., which don't provide really value for the other side. So what we can see from this scatter plot is actually not much. Most of the pull requests here, and I think this is a data set of 500 merge pull requests, is that most of the pull requests have less than 500 lines of code, and let's say less than 12 non-trivial comments. But the scatter plot got me into thinking. It's that one thing that I was curious to understand from this perspective was what happens in the cases when we invest, let's say, a week and we produce a pull request of 1,000 lines of code, and we get back, looks good to me, or just 1 or 2 comments, and compare that to a pull request that has, I don't know, 30 or 50 lines of code, and we have a bunch of comments that we get to experience back and forth. So when we normalize the y-axis by size, and here we see the engagement per size, which is the number of non-trivial comments by 100 lines of code, is that, and this is something that, to be honest, I wasn't surprised to see, and it's like part of folklore in the industry, that the bigger pull requests tend to have way less engagement. But what we can see is that as we increase the size of the pull request, the amount of engagement per size tends to reduce. And this is interesting because the reason why we're using code reviews is we want to actually embed the human judgment in the whole delivery process. And what we're saying here is that if we don't even get the feedback or the amount or the extent that we would expect to get, then we are also not able to build the quality in. So I'm not saying anything about the left-hand side. I'm not saying that if we have a lot of feedback that, or we unlock the throughput of the feedback, so to say, that we get to have quality. But what I'm saying, if we have a process that relies on getting feedback and we're not, in order to be able to build the quality in, and we're not getting the feedback, then we're also not, or we're less, have less ability to build the quality in. So that's also one of the reasons why I really like this code. Never had a huge pull request that didn't look good to me. So apparently all of the huge pull requests look good to us, and it's kind of natural in a sense, because when you get a pull request after a week of work that is 1,000 lines of code or whatever size, that is huge, the thing has already been done. There's not much you can do about it. You're not able to course correct. The authors also got so much emotionally invested, sunk cost fallacy kicks in, that it's very difficult to steer. So what often happens is we just stamp or slap RGTM, deploy to production, and we hope nothing goes wrong, which often does. Or if it doesn't, then we just accumulate the risk over time that eventually materializes. But there's also interesting tweet that I found a bunch of years back is this 500 lines of code looks fine, 10 lines of code, 10 issues. And the thing is that the smaller pull requests, the people or reviewers feel that they're able to build the quality and they're able to intervene. And that's also one of the reasons why we get to get that feedback on that size of the pull request spectrum. So now going into the wait time, this was where most of the surprises for me happened. And if we follow this ticket number 1 from Emma, and then if we look at the bottom of the slide, we're going to see wait to processing time ratio. So if we just follow the cycle time or life cycle of the ticket number 1, we're going to see parts of the life cycle where the ticket is being actively worked on, which means Emma coding or Luca reviewing or Emma embedding the feedback from Luca, etc. And there is also a chunk of the time, which is a gray one here, which is a wait time, which signals the amount of time that the item just spent in a queue waiting for someone's attention. So waiting for Luca to answer or Emma to integrate feedback, etc. And to give you just a sense of what the numbers usually look like, what the encounter is for this data set, let's say of 500 pull requests analyzed, the amount of, and it took for this data set or for this team to push these 500 merge pull requests through the system of work around 6 months. The amount of cumulative wait time in months was multifold. And these numbers are not precise per se, but they are sufficiently accurate to be a good conversation starter when it comes to the process and the ways of working. So going into the scatter plot for the wait time, now on the y-axis we can see the wait time in hours. And one more thing that also popped up in my mind in this case is that, if you imagine that you invested, let's say, a week of effort, and then you wait 2 days for a review, it's not the same as when you invest, let's say, a half an hour or an hour, and then you have to wait 2 days to get feedback and be able to merge the pull request. Because the relative cost or the relative wait time when you compare to the size is pretty much different. So what happens if we normalize the y-axis by size and we get to see observations for the minutes in lines of code? This is the thing that I observed in all of the data sets where the teams have been doing async code reviews, is that as we reduce the size of the pull request, the wait time per size tends to go exponentially up. And that makes sense because the relative cost to effort, so to say, or the wait time to processing time ratio is different depending on the size of the pull request. And the interesting thing for me here is that the way that I interpret this is that this for me means that as we reduce the size of the pull request, the cost of code review per size goes up exponentially. And I'm pretty sure that I'm not the only one that experienced this, but one thing that I usually advise teams when I get into teams and observe a big pull request, and everyone wants to have a small pull request, is that I usually suggest to use the batch size or use a small pull request, which is a pretty good default intervention. And the reason for that, with a smaller pull request, it takes less time to write the pull request. It's quicker to review, less time allocation for the reviewer because I can squeeze in 15 minutes of review more easily than I can do for 1 day of reviewing a huge pull request. They tend to have higher engagement, as we also noticed, because people have a sense that they're able to contribute and course correct. They're also less risky because we change less things at the same time. And then if anything goes wrong, it's also easier to troubleshoot. And when it comes to the DORA metrics, they also positively contribute to all 4 DORA metrics, right? But then what I'm saying now is actually there's a trade-off, right? So as we reduce the size of the pull request, the cost of code review per size goes up. And the way that they see this is actually the system is pushing back against us when we try to reduce the pull request. And one more way to understand this is some other scenarios. For example, if you have a test suite that takes, let's say, 20 minutes to run. If I have a test suite that takes 20 minutes to run, I'm not going to run test suite after every line of code change. Why? Because it doesn't make any economic sense, right? So the system is essentially sending me a strong signal as I'm reducing the size of the pull request. Hey, the cost of getting feedback from tests is really expensive, so use it very wisely. So what I do, instead, I increase the batch size, increase the amount of changes that I introduce before running tests, which means that I slide back into the bigger batches in order to make economic sense out of the whole process, right? And one interesting thing is that what they're trying to say here is that small changes are inhibited in this kind of environment. So trying to refactor in this kind of environment is really difficult or close to impossible because people have to wait disproportionately longer time for reviewing a smaller change, right? So what usually happens, people either don't do it or they accumulate it in a bigger change, right? And the thing that they observe, this is a qualitative observation, is that the teams that have lower latency in communication are the teams that also have a healthier code basis because they're able to continuously refactor the code and align it with the shared mental model that they have together as a team. And that's a really important point because the intervention point for reducing, so to say, the craft in the code is reducing the latency in the whole process instead of trying to create a huge Excel sheets with to-dos or any points that we need to tackle, which is often doesn't help. But the general point here is that inventory expands until it matches delays in the system. So think about the inventory as a manifest of the invisible part, which is delays in the system. So what you can usually observe is that the inventory starts piling up in the places where there are systems between the delays between the actors in the system, right? So one way to hunt the delays is trying to look for the amount of inventory in that stage. And that's also one of the reasons why I really love this quote from Don Ragnarsson, which is, while you may ignore economics, it definitely won't ignore you. So try to think about it more actively when you're trying to change the design of the ways of working. And when it comes to the systems, and there are lots of talk about the systems thinking, but it's really interesting that you can sense so much feedback, rich feedback and qualitative feedback from the system in multiple ways. And I'm going to also mention one of those today. So if you got to notice this comment here from Emma, can you review my pull request, please, with his begging hands? I noticed that people tend to beg, so to say, for reviews of pull requests in so many different ways. And that's one of the reasons why I tend to say the amount of bagging in the system is proportional to the working process. So what I mean by this is that in the systems that are loaded in terms of utilization, the size of the queues increases, the delays increases, and then people try to push their thing that is waiting for someone disproportionately long by trying to nudge them and pull them by the sleeve, so to say, as Emma was doing here with Luca. So you can, by the amount of bagging that you observe in the system, you can tell a lot about the amount of the working process and the utilization rate, so to say. Now, switching gears, going into the flow efficiency. So this is also one of the metrics that comes from Lean, and just short refresher for anyone that is not familiar with it, but the idea is that we try to understand how much of effectively we work on an item during its cycle time. The higher the flow efficiency, the less the item spends proportionally waiting for someone. So the higher the flow efficiency, the better process, and vice versa. There are lots of things when it comes to flow efficiency that are not as good, but as a metric, but it's really informative in a sense to try to get to understand different processes. So here we can see this is also one of the plots on the y-axis. I'm not going to go into what this exactly means, just approximately to the flow efficiency. But what's interesting to see in all of the data sets that analyzed is this behavior where the flow efficiency starts plummeting at one point. And this is really interesting because if you do a thought experiment, and let's say that you have 300 lines of code that you need to, as a change, that you need to push through the system of work. And let's say that you have at least 2 ways to go about it. And one way is splitting into 15 PRs, small PRs of 20 lines of code. And the other one is just doing a big PR, 1 PR of 300 lines of code. What this curve is telling us is that the cumulative lead time that is going to take us to push 15 PRs of 20 lines of code through the system of work is going to be way longer than the cumulative lead time is going to take us to push 1 pull request of 300 lines of code. So no surprise that people, tend to increase the size of the batch when they get to experience delays in the process, right? So just intervening in a way of saying to managers, calling out engineers and asking them to be more professional, whatever professional means in this case, is a really really bad intervention, I would say, without a deeper understanding of the whole problem. But the problem is in the whole process, so to say, the way that the ways of working was designed in the first place. And it's nothing about the individual, but about the system in a sense. So here, the way to interpret this is actually, as we use the size of the pull request, we start accumulating more wait time as a percentage per unit of effort, so to say. And because of that, the lead times also go up on a cumulative basis, and the throughput also tends to drop. So that's the reason what we tend to, or we lose the throughput on the smaller pull request size, right? And one interesting way to also reason about it is that the promise of the async way of working is actually that you can start working without the other people that you are going to depend on not being available at the time, right? So what happens in the system when you make the cost of starting work 0, because that's essentially what we're doing with the async work, where essentially what we're doing is we're increasing the arrival rate of the work because we're tilting this towards the higher arrival rate. And then because of that, we get to experience more working process in the system. And then because of that, we get to experience longer cycle times and lower throughput. And even more, there are lots of second and third and fourth order effects of this problem. And one of those is that the high working process invites even more working process. So you also saw it with Emma, where she was waiting for Luca. Luca was not responding. So while she was waiting, hey, let me start working something else. Because when you're blocked or when there's lower responsiveness in the system and the higher wait time, then we humans are really good at piling up inventory and pulling in even more work, which kind of exacerbates the whole problem even more. So what we're saying is that on one side, we are not able to build in the quality, and we're also introducing delays. So it's like a lose-lose in a sense. And then on the other side, we also lose throughput if we reduce the size of the pull request. So we're kind of faced with trying to make a trade-off between losing throughput and losing quality with the async code reviews. And for anyone that has been familiar with the work of Donald Anderson, and this is a batch size optimization U-curve from the book, his book, The Principles of Product Development Flow, maybe this trade-off kind of reminds you of that. What we're essentially talking about here is this transaction cost, this yellow line, but this trade-off that we're trying to make and find the optimal batch size is based on this overall cost in the system. So me kind of growing as in seniority, so to say, or in experience as an engineer, I always heard this quote, and I used to say it more and more often. There's always a trade-off, but what I got to also understand is that that's true and likely, but that doesn't mean that you're not able to affect the trade-off forces, because some trade-off forces could be influenced in a way that the trade-off can be approximated to a win-win, right? So there's still a trade-off, but you're able to change the forces that it doesn't appear as so. And when we talk about this, it's hard not to mention the Dota Research and Accelerate book. And the biggest myth that I think the Dota Research debunked is that it's this idea of either throughput or stability, this trade-off. And what the research essentially showed was that it's both throughput and stability. So if you so both of these go both up or they go both down, and that usually reminds me also of this idea of the quality versus speed, for example, which we're touching upon here. And I do believe that we can also have our cake and eat it too. So let's try to work backwards from the problem that we have, all right? So what are the things that we can do when it comes to this way of working that could help us to keep reducing the size of the pull request, because we want to have smaller batches, but we don't want to incur the exponentially higher cost of code review per size, right? So what happened is that because of this exponentially increasing cost of code review per size, the throughput plummeted, right, as we reduce the size of the pull request. And what we want to do is we want to keep reducing the size of the pull request, but we don't want to lose throughput. So let's work backwards from there. So if we don't want to lose throughput as we reduce the size of the pull request, obviously we should not or must not increase the cost of code review per size as we reduce the size of the pull request. And in order to be able to do that, the actors' reaction time, whereby actors, I mean authors and reviewers in this whole process, their reaction time has to be exponentially faster and faster and faster to each other's request as we reduce the size of the pull request in order not to incur higher cost of code review and lower throughput as they reduce the size of the pull request. And in order for them to be able to do that, their availability needs to go up exponentially, right? Because as you saw it with Emma and Luca, they weren't able to react sooner because they were busy with other things, and there were lots of things that were competing for their time, in a sense, right? So if we go back to this visual and we just pull up this ticket number one and look at delays that we have involved in the ticket number one, and let's say that their average size of the pull request is this much. So what we're saying essentially, if we want to reduce the size of the pull request, but we don't want to lose the throughput, Emma and Luca need to react exponentially faster and faster to each other's requests, essentially to a point where at one point they would need to even work together, so to say. And this is essentially a conclusion of the study that is that in order not to exponentially lose the throughput while reducing the average size of the pull request, people need to get exponentially closer and closer in time. And that leads us to essentially a continuous code review. So talking about the continuous code review and thinking about what are the ways of working that we can employ that we get the continuous code review as a byproduct of working together, right? And I call this, so I'm pretty sure at least some people have heard for pair, mob, or ensemble, or software teaming, as it's also called these days. I call them jointly co-creation patterns. So where we get to sit together and work together on the same thing at the same time. And what's really interesting about this way of working is that the way of working by design provides availability, guarantees availability of the reviewers in the whole process, which means that you're able actually to keep the wait time to zero, right? Not to have it at all. And the other also thing, which is really interesting, is that the teams that don't work together or they work in isolation, they tend to pile up a lot of work in process. So multiples of the number of people that they have. But when you work together, let's say that you're pairing and you have 6 people in a team, then you usually have the max working process is 3 items, right, instead of 12, for example, which is a 4 times reduction in the working process. So there are lots of things which I'm not going to go into today because I don't have time for that when it comes to second and third and fourth order effects of working together. Yeah, this is one of these, which is really interesting, because what we're saying here is that we're able to, because we work together by design, we reduce this transaction cost, transferring a batch from a coding to a review, all the way to the minimum batch size. So we are essentially able to push the optimal batch size all the way to the left. So going back to this point that I made, it's still a trade-off, but we change the forces in a way that it doesn't look like as one anymore. So thinking about, okay, so what are we trying to optimize for here? And you should feel free to optimize for whatever you want, so to say. But the things that I tend to optimize for in this whole process is we would like to have a smaller size of the pull requests, so smaller batches, but we don't want to lose the throughput. So we need a wait time per size also to keep going down or stay constant. The engagement per size, we don't want to lose it because it's a precondition for being able to build in the quality through the human judgment. So that's one of the reasons why maybe also saw it on some of the scatter plots as a sidebar. But this PR score is just trying to capture the relationship between these metrics. So it's one number gives you one of the ways or one of the angles of looking at the whole problem, but it's size times wait time in minutes divided by 1 plus engagement. Now it's 1 plus engagement because I often get to see 0 non-trivial comments and no one wants to divide by 0, right? So the thing here is that if you employ co-creation and you work together, the size of the pull request can be as low as 1 line of code, or it's at least a minimal or atomic change that you make. And the wait time in minutes is 0 because we have guaranteed availability. And in the engagement, it's actually not as important, but it often goes up even more because the latency in the whole process is reduced, and we also get to provide feedback in a face-to-face manner. So this whole thing for working together actually evaluates to 0, which is essentially the best score for this kind of optimization that you can get. And that's something that I usually find kind of really interesting, because that's also one of the reasons why I tend to say that the optimal size of a pull request is 1 line of code that is reviewed as it's being typed. And I honestly still don't know for any better way to achieve it than by pair, mob, or ensemble programming. And I'm very much on the lookout for any other practices to learn, which help us do the same thing. But this is, I think, if you're trying to optimize for these things, I think these are probably the best base case or defaults that you can choose, so to say. So talking about the PR score, here it's plotted for one of the data sets. And what you can observe is this cloud, and the y-axis is on a log scale because the results were so big, i.e. so bad that they had to use the log scale. And this is usually one world that they get to observe. Teams doing async code reviews. And then there's the other world that I get to observe, which is this continuous code review, pure mob programming, which is very much distant, as you can see on the log scale between these two worlds. And I wanted also to share one of the stories that with one of the teams that I was working. It was a team that was built around XP practices, so all the XP practitioners, and we were doing mob or ensemble programming by default, really good design skills, continuous refactoring, trunk-based development, TDD, etc. And at one point, I figured out, for some reason, the idea came up to just look at the Git log and try to understand how often did we get to push the trunk in a day. And one of the examples was this time span of 9 hours and 20 minutes, with some breaks, of course, in between and lunch break, etc. But what we get to observe was that the number of PRs merged, and PRs is under quotes because it's not really PRs, is because we were using trunk-based development. So every commit that we made was landing on the trunk. It was 107 PRs merged, so to say. So for a team of 5 people, that's a completely different world than what we get to observe otherwise in work in isolation, right? And the median time to integrate, so since the start of the change until it landed on the trunk, was 2.3 minutes, right? So every 2.3 minutes, you had a new change that we were able to deploy, and every change was in a deployable state. The deployment pipeline wasn't even able to keep up with the amount of changes that we were able to push through the system of work, so to say, through the delivery pipeline. So we essentially shifted the bottleneck to the deployment pipeline, which is a really good problem to have in the first place, right? But in order to do that, it's not only working together. There are also a couple of other practices, XP practices, that play together to be able to achieve that. But no one was trying to optimize for this. This was just a byproduct of the ways of working, right? So that's also why I like to say that this dude Mark Twain also said for that time, they didn't know it was impossible, so they did it. So I think there's a lot of skepticism about XP practices, and is this really possible? But from my experience, it is definitely possible to achieve it. And yeah, with some coaching guidance, etc. Definitely, I think it's very possible. So throughput or quality, I would say both throughput and quality. I think we need to reevaluate these ideas of the trade-offs and using it as a card for not diving deeper into understanding what are the trade-off forces that we have, and can we affect some of those, and how to change these economics of the system, so to say. So we might move to a win-win situation instead of not considering that in the first place at all. So yeah, with that, I would like to say thank you for coming today and sparing time to attend the talk. I also wrote an article for InfoQ a couple of years back that got a lot of 2022, yeah, a lot of traction in the community, and I think there is a lot of need for discussion. That's what I sense in the community about these things, because lots of developers are really experiencing pain, and on lots of DevX, so to say, questionnaires, I get to observe the pain with the wait times for pull requests being one of the top most pain points, so to say. So yeah, if you're interested, feel free to check it out, and I'll be more than happy to connect with you on any of these social networks. And with that, I would like to, yeah, again, thank you, and we can open the floor for any questions you might have. Thank you.
Thank you, Dragan. This was great. Just maybe my comment on all of this, like it goes back to what Dave Snowden and others said in the previous discussion about, designing for those interactions. And I think designing for interactions where people are actually getting closer together and like doing this is one of those patterns that they discussed. There are 2 questions in here. So Mark's question, and again, I could be missing, so repost your question, but Mark says, Dragan, what are you equating or including for transactional cost in your dynamic U-curve slide? Some, not me, would believe that cost is doubled with pair programming.
Yes, so this is a typical question that I get to hear. So what we have on this batch size optimization U-curve is the transaction cost, which is a cost of transferring a batch from one stage to another. So in this case, it's from coding to a review, right? And the more delay there is, the higher the transaction cost we have. That's the reason why we see this exponential increase in cost. Now, to the other question about the doubled cost of working together, it's really important. So there's a really long answer, which is theory of constraints, which is going into throughput accounting versus cost accounting, because the idea of the thinking first about the cost is a signal about the cost accounting mindset, which is something that we try to move away from. But think about, instead of the costs of the people involved, think about the cost of a delayed feedback. Think about the cost of a delayed value to the customers. Think about the cost of increased or decreased learning cadence. How often do you get to learn? And a bunch of other things that you get to experience if you delay delivering value to the customers or delivering the experiments. So what I'm going to say is that these costs, when you look at them, and there are more than, I counted at least 10 of them, is that they tend to dominate the cost that you get to observe with thinking about the cost of people being involved in this whole process, right? So the whole idea is trying to shorten or minimize the lead time to make an impact, minimizing lead time to get to a value. So I would tend to recommend to try to optimize for that.
Okay, and then Ryan had a question. How does one work towards minimizing groupthink in pair mob programming context?
Yes, I think there was also I think this point was also raised a couple of times, and I think Woody so one of the pioneers, so the inventors of mob programming, also wrote about it on a couple of occasions. But I think it also goes with psychological safety, being able, radical candor, and being the ways that you also facilitate the group work, so to say. I think it plays a really important role when it comes to that. So you're able to service all the, and how do you handle the power dynamics inside of the team, etc. So these things are skills to learn. It's not just let's jump everyone on the call and just think that we're doing something and call it mob programming. It's not really. There's a lot of skill that needs to be involved when it comes to coaching and facilitation on these patterns that kind of help with counteracting that. But good question, definitely. Yeah.
Any other questions? Maybe while just type it in or just go off mute and ask. But another thing that a lot of times I see, at least, is people reluctant, like, especially, people that are not used to pair programming or that don't have environment, like without psychological safety. Like, what are some of the ways that you found to get people more comfortable and open, and also to educate and leadership and people maybe with lack of background in programming, to understand that it doesn't cost more, that this is actually better way to do,
Yes.
What have you found works in convincing other developers or programmers as well as leadership?
Yes, even when you think about the cost, what we're saying is we're actually having lower costs with this. If we think about the cost of delay and cost of value, etc. So even if you want to optimize for that first, then you also get lower costs. But when it comes to psychological safety, and I think that's the important point. I often get asked by engineering managers, yes, we would like to try this way of working, or we would like to do it, but I'm not sure that we have enough psychological safety. And I think, if you have a problem with psychological safety in a sense of highly dysfunctional group or toxicity, then you have a bigger problems to solve, right? But if you're a fairly functional team, so to say, then what's really interesting is that actually these ways of working help you build a psychological safety as a byproduct of that. Because when you think about it, the pull request, as I get a pull request, is the end result that they get a polished work from someone I don't get to see all of the mistakes that they made. I don't get to see all the paths that they decide not to take, etc. But when we get to work together, then we get to also have an environment that we're able to express the vulnerability, because suddenly you see me making all of the mistakes that I'm making, right? So we need to build acceptance and trust between us in order to be able to work together. And it's a really great way actually to build the psychological safety, or start building the psychological safety, because I think actually the environments where you're not even able to be vulnerable, and I don't think that working in isolation and throwing things over the wall is that kind of is actually that kind of environment. Then you don't even. I would say it's a question if you even have a team. So I think finding ways of working that enable us to exercise vulnerability is really important as a way to build a psychological safety. And the more psychological safety we have, then the more even desire to work together. So it's like a reinforcing feedback that feeds off itself. So the long answer to that question is, if you need psychological safety to start working together, then start working together
Yeah.
in order to have more psychological safety. Yeah.
Exactly, yeah, because it's like I agree. Like the more that you're vulnerable and the more that you're, working closely with people, the more likely you'll build trust, not through,
Yeah.
Have you seen this pattern applied outside of software development, or just the pattern of getting people closer together, shorter feedback loops? Because I'm assuming this applies not just to programming, but it would probably apply to other disciplines. Or are there other parts of the value stream, or because again, if you look at just development, it might be part of a bigger value stream network. So any
Yes. So I think outside of our industry, I don't have much experience, but I think we are very special in that sense that we tend to work in isolation way more than other industries for some reason. But then when it comes even to our own team, so to say, if we involve the product development teams with product managers and designers, etc., I think lots of other functions are way more used to working together for some reason than what we get to observe. And there's also, I think, a long answer to why people tend to prefer often working in isolation. There's a lot of incentives, etc. I won't go into that. But yeah, I think there's so many, like when you think about also design thinking, design sprints, so many of these conversations are actually ways of working together, considered, rather than just throwing things over the wall and using documents to throw it at each other instead of having a face-to-face conversation. Yeah, I think there was one more thing that I wanted to say, but yeah, it's also interesting that when it comes to the DevOps moment, and in the sense of trying to automate the pipelines, I think everyone now understands the value of that, and because it reduces this transaction cost to deploy something. But for some reason, we didn't translate this whole learnings of reducing the transaction cost into the pull request or the code reviews process. So I think that's one more step for us to go in order to kind of have a faster flow of value through the whole value stream.
Yeah. Good discussion. I don't know if we have a few more minutes before the closing keynotes by Dave, but any other questions, thoughts for Dragan?
I would offer just a compliment. Like I really love your application of TOC thinking to the code review process. Since I've encountered it, I've leveraged it quite a bit to try to influence change. So thank you for your work.
Thanks, Simon.